It's 11 o'clock local time for all of you, except Portugal. That's 1 hour later. So it's 11 o'clock local time here in the Netherlands. I welcome you. You can see me here on the screen because I switched on my camera. I think that's nice to do in the first minutes to give you a warm welcome on this second webinar. And I think most of you already have seen the first webinar a month ago. And it's all connected to the high impact weather summer online course for EUMETCAL. And what I can see from the names who are in now at the moment, that most of you has already sent their exercises to me. So thank you for that. And you already received the key exam. A few of you already sent the exam results this morning. So you will receive the exam key this afternoon. Okay. I will now switch off the participant list so that you are able to see the slide in a full sense without having any yellow blocks or things like that inferring the image. So I will switch it off now, but before that I first switch off my camera. Okay, I will start. Well, a little bit about the content. Oh yeah, and on the first slide you can see a sort of time window that it will take about 1.5 hours. I will speak about 1 hour and 10 minutes, that's my guess, and then we have 20 minutes for answering questions. Okay, a little bit about content. Well, based on the first webinar, I will give you firstly a short summary of the convection scheme, because I think that's the most important part of this online module, that you are going to use that convection scheme. And then I will show you a short case study with many thanks to Paulo Pinto from the Portuguese Weather Service. And then I will jump over to an actual case study about a convective case that happened last weekend, and especially what happened yesterday on Sunday, May the 2nd, over Central and Eastern Europe. And from the participant list, I can see that there are also some participants from that area. So I think that's nice that they have their own experience from that convection from yesterday. And after that, I'm going to discuss some important details about the most important high impact weather phenomena. Okay, we are talking about the ingredient-based forecasting. I showed you this image before, and you can find this image in the course material as well. And well, it's all about that you are working in a specific way in looking at convection, and because physics works the same all over the planet, you can more or less work in a sort of procedural way by looking at ingredients. And the strength again of this methodology is that you not only looking at index or indices, because that's a black box in practice, but that you really looking at the physics behind the processes that can lead to convection. Well, this is the convection forecast scheme, and I hope that you already have gone through the material in which I showed you on the hand of some presentations and some reading material how to use this scheme. And today we are going to focus on a few case studies. The first one in Portugal and the second one that happened yesterday in Central and Eastern Europe. And we are going to look at the three ingredients: moisture, instability, and lift. And we're also going to have a look at the wind shear to determine the convective mode. And afterwards, we are going to talk about a little bit more in detail about the different high impact weather phenomena, like heavy wind gusts, heavy precipitation, hail. So that's, I think, a very nice program for the next 1.5 hours. Okay, a little bit more about a case study Paulo Pinto produced a couple of years ago. And well, if you look at the three ingredients, then we talk about moisture, instability, and lift. You can, in the convection scheme, you can look up all kinds of detailed parameters you can look at to determine the amount of moisture, instability, and lift. Well, if you finally determined the three ingredients, then you can also add the amount of wind shear into the convective scheme, and that will finally determine the degree of organization. Well, if I start by looking at the first ingredient, that's moisture, then for instance you can look at the relative humidity at the different model levels, but you can also look at wet bulb potential temperature at the surface, or what I normally do at 850 hectopascal height. And I have to say, it's not and you can also look at the amount of water that is hidden in the troposphere, and that's called precip water. And in most tepigrams, you can in most forecast offices in Europe, what I've seen, they already in their meteorological workstations, they can look it up, the amount of precip water, by looking at tepigrams or calculated tepigrams. That's the so-called proc soundings. Well, if you look at instability, you can of course look at CAPE, and if you look at lift, you can look at all kinds of lifting mechanisms. I mention here one very strong lift mechanism, that's the jet streak. And that also will come into play during the next two case studies. And for determining wind shear, you can look at different kinds of heights. What is normally done as a sort of first estimate is to look at the lowest 6 kilometers to determine the amount of so-called bulk shear. But in the end, it's more important that you look at the effective wind shear. So that means that you look at the layer in which the convection takes place. And that's not always from the ground, as you have learned in the meantime. And in the end, you are trying to find an overlap area. So you combine moisture, lift, and instability, and also wind shear. But apart from wind shear, you can start looking at the first three ingredients and to find an overlap area. And in that overlap area, that's more or less the area where the ingredients are fitted right or in the correct way. So that combination will give you a sort of first sign that convection will probably happen in that area. Okay, I first show you the first case study. It's not in summertime, but actually in wintertime. It happened in November. And we have to concentrate, I hope you can see my mouse. We have to concentrate here in the area of Southwest Europe, of course, Portugal. And what you can see is an upper air map with the geopotential height 500 hectopascal based on ECMWF. And you can see quite an active low pressure system, cut-off low, just to the west-southwest of Portugal. And what is important when we zoom in is that we, apart from looking at the upper air charge, we're also looking at the amount of moisture. And what you can see that in the southwesterly flow, there is quite an amount of moisture available based on the warm subtropical air mass. And if you look at the different levels, you also can retrieve some amounts of CAPE in a range of 300 to 500 joule per kilogram. And there's also a vertical profile that's in the extreme south of Portugal. And from that, based on the ECMWF, you can see that there's CAPE available, just mentioned, in the range of 300 to 500 joule per kilogram. And in potential, there is some convection possible from the ground. So that's called surface-based convection. That's very important because in the next case study, after this one, I will also show you areas where you cannot have convection from the ground. So then it depends on the so-called elevated convection. So it's always important to have a sort of clue or idea when you're studying convective situations in your forecast office to determine if convection is possible from the ground or from some certain level. Well, in this case, it was possible from the ground. Well, what is very important is the jet streak. It's quite predominantly, you can see it here on this map, and you can also quite nicely see the maximum in wind. And you can see the left exit of this jet streak, and that's entering more or less the extreme southwestern parts of Portugal. Well, you can look at all kinds of thresholds. You can look it up in more detail, but the more shear you have, of course, bulk shear, but also the more detailed shear in the lowest levels, the more significant weather you can expect in terms of more convective organization. And the lowest shear, I will not go into detail about that, but that's important for the development of tornadic circulations. Okay. Oh, sorry. Yeah, as you can see here, there's also an amount of bulk shear over the southern parts of Portugal. But what is more important, I think, in this case study, is that you can combine all this information by using that convective prediction scheme. And that means that we have to look at an overlap of all the three ingredients, including wind shear. So we are looking at 4 areas. And when we do that, you can see the moisture, you can see the lift due to the left exit of the jet streak. You can see the area with the highest instability, so the most CAPE, and you can see the area with that's wind shear. Yeah, and when you combine, you can see a sort of overlap in the dark red area, and that's that's moving into the outskirts, the southwestern outskirts of Portugal. And in this case, even a few tornadoes occurred in that area, so that was quite unusual. So that's of course, the reason that Paulo Pinto used this case study. Okay, this is, I think, a nice example of just looking at the ingredients and to find an overlap of instability, lift, moisture, and the maximum amount of wind shear. Well, this methodology I will apply on a case study that happened this weekend. And this weekend, quite nice convection occurred over some parts of the Balkan region, the central eastern parts of Europe. And what you can see on this slide is an image based on the EUMETCAL map viewer. I hope you all are familiar with working with it, because apart from your own meteorological workstation in your own forecast office, it's, I think, a perfect map viewer just to prepare yourself on what is going to happen, or to have a clue about a sort kind of analysis of what is happening in the atmosphere. And what you can see is the situation from yesterday. You can see the date and the time in the upper right part of this slide. It's the Sunday, May the 2nd, and this was 6 UTC. And what you can see in blue is the 300 hectopascal geopotential height. In black, the mean sea level pressure lines. In red, the wet bulb temperature 850. And in the background, you can see a high resolution visible image. Well, the first question I'm going to ask you is, where do you think, based on this information, is the most interesting area related to convection? And maybe, Tomislav, can you give the audience the possibility that they can show me the results by using a pencil? Approve?
You can do that by clicking the annotate.
Oh yeah.
In the top.
Yeah.
And allow all.
Allow to annotate.
Or if you just click everyone who wants to click that.
Allow to annotate.
Allow to annotate everyone. Something like that.
Oh, I could not see that possibilities. Approve doing the... You and six other participants can start annotating. Allow to annotate. Oh yes, okay. I think everybody is now able to annotate.
Yes.
Yeah, in the image. And I can already see some interesting information. Please take your time. I will wait a minute so that all of you has giving in their area where you think, yeah, most of the convection will take place. And will take place, I mean with that, in the course of the Sunday, course of the day. This is 6 UTC. Okay, it's quite interesting. Because I can see, yeah, there's also an interesting green area. Yeah, and I think most of you already take into account the development in the course of the day, because what you can see on this map is a quite vigorous low pressure area. Here somewhere over Hungary, the eastern part of Hungary, Slovakia, and that's moving to the northeast. So most of you already have indicated an area to the northeast of that low pressure area. And so that means that that you expect there most of the convection. Well, that's the correct answer, but I can also see some other areas to the south, and that's also an interesting area. That's more or less in the warm air. And well, I will show you the results, of course. But first, I want to emphasize. I want to emphasize that by looking at this map, okay, we can stop now. Stop annotating. Yeah. By looking at this map, you can more or less, roughly speaking, can see the three ingredients. Because we can look at the 300 hectopascal geopotential height. That gives you a sort of clue about if you can see some curvature in the isohips. Well, indeed, you can see some cyclonic curvature here just over the overhead the area of low pressure at sea level, and so that produce, of course, lift just to the east of a so-called trough. But there is also a jet streak into play. You cannot derive it. Yeah, you can more or less roughly derive it from this image by looking at the distance between the isohips, because there is a jet streak to the southwest in this image. And well, the left exit of that also played an important role yesterday by producing convection. So lift, there is enough lift. If you look at instability and moisture, well, instability, you cannot directly derive it from this amount of information, because you can also look at some certain levels in terms of geopotential height, in terms of isobars, and in terms of theta W, so the wet bulb potential temperature at 850. That's drawn in red. So in terms of moisture, you can more or less see an axis of a maximum theta W values, ranging from Romania into the Slovakia, eastern part of Hungary, into the extreme south of Poland. This was a situation with quite a strong temperature gradient, as you can see. If you go a little bit to the north, you can see that you end up in much colder air over the northern half of Poland and the eastern part of Germany. Lithuania, thank you. Oh yeah, that's now. Yeah. Well, that was quite a strong temperature gradient. Well, it's interesting to look at some more detailed information to figure out what really happened yesterday. So I go over to the next slide, and you can see the weather map. You can see that on the weather map at surface level, quite distinct warm front. You're over the south of Poland into White Russia, and a cold front connected to the low pressure area here over eastern part of Hungary, moving into Slovakia, into just over the western est of Romania to the south. That was the situation at 6 UTC, and when I zoom in, you can more or less see in combination with the high resolution visible image, you can nicely see the cloud pattern, especially the cloud pattern connected to the warm front. That's a slow gliding up of warm air over cold air over Poland and Germany, and that produced a lot of cloud and heavy precipitation. And more to the south, especially in the warm air, you can see more fragments, sort of interchange between clearings and some fragments in clouds. But what is more interesting, if I overlap this information with the observations, the synops, And then you can see at, this is not 6 UTC, but this is 6 hours later. This is 12 UTC. You already can see some convection taking place in this area. There's convection here along this trough at the ground that's connected to the cold front. And along this cold front, you can see already some convection taking place. And look at the temperature difference. You can see some relatively warm air here in the south with temperatures in the 20s, and much colder air, very cold air to the north with temperatures around 6 or 7 degrees Celsius, with a lot of precipitation over there. Well, it's interesting to look into a little bit more detail about what is happening here along the cold front, but also in the end what is happening in the cold air here along the warm front, because there was more than one area where convection was able to develop. And in this showcase, in this case study, I will show you the importance of firstly looking at the convection scheme and zooming out and looking at the areas of moisture, lift and instability, and then zooming in and looking at epigrams or soundings, and to determine where convection is able to be ground-based and is elevated. Because in this situation, both types of convection occurred. Well, if I go over to the next slide, then I produced a cross-section, which you can easily do in this EUMETCAL map viewer. And I hope you can see it, but this I've chosen for a vertical cross-section that starts here in the west-southwest, and that's moved through the cold front and ends up here to the east, somewhere in White Russia. And what you can see from this vertical cross-section that is shown here in the right lower level of the slide, I hope you can easily see the most warmest air here, just before the cold front. And I've combined the potential temperature field with the omega field. And you can nicely see a lot of upward motion just ahead of the cold front and on the location of the cold front, and some descent motion at the backside of the cold front in the less warm air or colder air. So you can nicely see the warmest air that's that's just ahead of the cold front. And on the map itself, you can recognize the warmest air in the sense that a tongue of highest delta W values at 850 hectopascal is visible over there. That's more a sort of first estimate of the air where most energy is hidden in latent heat. So as soon as convection will be released, that you know that along such a tongue of maximum theta W values, you also always end up with the maximum amount of latent heat. So that's also very important to take into account. Well, if I go over to the next slide, then you can nicely see the same image at 12 UTC, but now I added the isotex at 300 hectopascal. And then you can easily see the jet streak here over Italy, moving into the central Balkan countries, with a left exit region over here, just to the southeast of the low pressure area. If you go over to some radar images, this is radar images in the early afternoon, around 13 UTC, so 1 hour later than 12 UTC. You more or less clearly can see the convection along the cold front, that's around here, but you also can see some embedded convection over here, over and just to the north of the warm front. And I will come to that in a little bit more detail in a few minutes by studying the soundings, because in this situation, both type of convection, so ground-based, surface-based convection and elevated convection occurred. But furthermore, a little bit more to the south, you can also see some discrete cells, more on the border between Romania, and these were very active with a lot of lightning, moving into the western part of Romania. Well, you can also see it here on this nice satellite image with the cold front and also the discrete cells to the south. Well, if you look at it in a little bit more detail, then I first show you the sounding based on GFS, which I pinpoint just at the location of the cold front. You can see the location of this sounding in the red dot on this small map. And what you can see that there is a little bit of a small inversion, but with enough lift, parcels are able to move from the surface all the way up. There is not too much cape. You can see that if you look at surface-based mixed layer and most of stable cape, that it has a range between, let's say, roughly speaking, between 100 and 500 joule per kilogram. But you can see nicely, if you look at the hodogram and also at the wind pattern with height, a nicely, slightly curved hodograph and a slightly curved pattern. That means that you have a slightly varying wind with height, and of course quite a strong increase of winds with height. That means that you have quite an amount of bulk wind shear. Well, that's along the cold front. If I look at the location where some convection occurred, embedded convection in the warm front precipitation, then we have to look at this sounding. And this is sounding in which you nicely can see the sharp temperature inversion, the frontal inversion, I have to say. And then you know that you have to deal with elevated convection. And that elevated convection that can take place in a satellite profile all the way up to the top of pass. And well, that's also nicely situated. And a little bit more to the south, in the direction of the more discrete cells, you can see nicely quite an unstable atmosphere where the warmest air is. And from this sounding, you also can see that there is quite an amount of cape in the range of 1200 joule per kilogram. And well, if you look at the Estofax forecast, then they already on Saturday, in their forecast they were mentioning the short wave trough in the mid and upper parts of the troposphere, and well, if you look at the general situation, they were talking about a rapid surface cyclogenesis, which we have seen on the weather map, and that's forecast ahead of the trough, and they are already mentioning the left exit region of a quite active jet streak, 100 knots, 50 meters per second at 300 hectopascal, and well, that trough in combination with the jet streak was enough to produce a lot of lift. And if you go a little bit in more detail, then in the text, if you look at the area of interest, that's from Romania to Belarus, then you can see that both type of convection, so the elevated mode and the surface-based mode, has been mentioned in the forecast that was written on Saturday, the day before. Well, there's also some details given in this text about the environment in terms of the low-level wind shear and also in the storm relative helicity. The storm relative helicity is not a component of this online course because the main focus is using the convective prediction scheme. But if you look into more detail about forecasting supercell convection, then of course the SRH, the storm relative helicity, is important. And if maybe you have noticed it, but the soundings I showed you already gave you a sign of quite high values of that storm relative helicity in the lowest 3 kilometers. Especially those discrete cells in the south, just to the north of the Romanian border, they had some supercell signatures in it. Well, this is also a sort of scheme I use in my forecast office at KNMI, that you can look at all kinds of phenomena that you can fill in your scheme to determine the amount of lift, moisture, and instability. But in the end, it is important that you zoom in at the local scale and that you look at, for instance, outflow boundaries. These are very important, and that's also the reason that we at KNMI, as a forecaster, we go over to make hand analysis to figure out where outflow boundaries are in combination with radar, and that is very important in the nowcast stage of convection. Let's say a couple of hours before convection will be released, then you have to look at all kinds of very detailed information. But again, you also have to take into account the more broader scale mechanism that can lead to lifting areas, like the positive vorticity advection areas, but also, of course, the topography, like hills or mountains. And you have to also take into account not only the areas of maximum TTW, but also to take into account the advections that can take place and that can lead to some higher dew points a couple of hours later, for instance. And again, and that's sometimes very exciting and unsure, that you have to determine if convection will be available from the ground, from the surface, or that it will be stick to elevated convection. Well, during nighttime it's quite obvious that almost all convection will be elevated, but during daytime it is sometimes quite a challenge as a forecaster to see if it is possible that convection is possible from the surface. Okay, that's this case study, and now I will go in a little bit more detail in the topics of high impact weather phenomena. And I will do that on the hand of those 4 phenomena. That's wind gust, that's excessive precipitation, that's large hail, and when we have time, also pay a little bit more attention to tornadoes. But the first 3, I think, is for this course most important. I also want to differentiate in this webinar a little bit between the single cells, also named ordinary cells, the pulse storms, multicells, and the supercells. Okay, well, if you look at the ordinary cells as a sort of summary, you do not have much shear. So the 0 to 6 kilometer bulk shear is typically very low, below 20 knots. And what is striking, that the duration is limited to half an hour most of the times, and that has to do with the fact that the cold pool that undercuts the updraft. In a low cape situation, you end up with single cells, and when you have more instability, so more cape, then you can have pulse storms. Well, you can see it in this scheme. You can see that in 30 minutes time, you can have the change from cumulus stage into major stage, and then half an hour later in dissipating stage. So the total duration is approximately between half an hour and 1 hour. And as you can see, the cold pool that develops as soon as precipitation starts will undercut the updraft. Well, the pulse storms, that's when you have more cape. They are able to produce severe weather. The single cells, when you have not so much cape, is in general only some precipitation. But pulse storms, again, they can produce large hail, a lot of precipitations, and also wind gusts. Well, if I start by looking at large hail, hail is, I think, for us as forecasters, but also so for the scientific community, still a subject of investigation, because if I start by looking at this slide, you can generally say that we have two types of grow regimes in an air layer, and that's a dry growth and a wet growth. And the dry growth, I will show you an image in a minute. That's when you have supercooled drop and it freezes completely on contact with a hailstone. And you have wet growth when you have supercooled drops which cannot freeze completely because there is a lot of latent heat release from the prior contact freezing. And I hope it will become a little bit more clear by looking at this slide, in which you can see the different layers of a cumulonimbus cloud. And you can ask yourself the question, where is the hail growth possible in a thunderstorm? Well, you can see the four areas again, with the most interesting area, of course, in the middle part, in which you can see between 0 and -20 an area with, in general, supercooled water, with some ice. And in the area between -20 and -40, you can see, widespread ice. And in very strong updrafts, so in very strong convective clouds, you also sometimes can see some supercooled water in that layer as well, with very low temperatures, so lower than -20. So you can see that it is very important that hail is able to grow in the different layers of the cumulonimbus cloud. Well, what determines the maximum hail size at the ground? Well, that all has to do with the amount of instability, the amount of cape, and the amount of cape determines the maximum vertical velocity. And in an ideal case, or in a case when you can expect the larger hailstones, you have a sort of maximum in your vertical velocity in the mixed phase region. And you can also say that in most cases, in 40 to 90% of hail mass is lost in falling from the melting level to the surface. And well, in generally, it's not so simple. So you can say that if you look at the mixed phase region, roughly speaking, between -10 and -40, and for the layer with the lowest temperatures can contain a mixed phase, so supercooled water as well, in case of cells with very strong updrafts. And the problem is that for updrafts strong enough to loft large hail, the small graupel particles will be expelled into the anvil soon after reaching the mixed phase region. And I lent this slide from the ESSL testbed, and it's For instance, Johannes Dahl has done some research in this topic. Well, in the end, you can say that for hail, there is still a problem that if you look at the growth processes, that the trajectory is not very well known or understood. But as a forecaster, the best indicator is to look at a combination of CAPE, lapse rates, and a freezing level. And then you can say, roughly speaking, that when you have a low or moderate CAPE, then it will mostly lead to smaller hailstones, while the moderate to high CAPE values will lead to some higher values of some bigger values of hailstones. And if you look at the very large hailstones, then you can say that in pulse storms, it's almost impossible to have such a large hailstone. And then you will end up with the supercell organization degree, where you can indeed find hailstones with a diameter more than 5 centimeters. Well, furthermore, if you look within the mode of pulse storms to excessive precipitation, then it depends on the rain rate and the duration that determines the amount of precipitation. Well, the rain rate depends on the CAPE and the amount of precip water in your layer, and the duration that depends on how it looks like in terms of propagation. And I will show you an image to show you what the components are that determines the duration of a storm, so to speak. Well, for the duration, you have to look at, of course, the storm motion, but also look at other factors like how the propagation is signed against the cell motion. And then you can, in a situation with excessive precipitation, for instance, you can have echo training. That's the third bullet point. When you have cell generation along a boundary parallel to the cell motion factor, and that can lead to a lot of precipitation because of a quite long duration of the cell moving over one location. So that can be of importance, but also backbuilding, that you have a propagation direction which is exactly the other way in comparison with the cell motion. So then that you end up with continuously new cells forming at the backside. And that can produce, of course, a lot of precipitation. And orography is, of course, also very important. Well, the wind gust, if you look at the wind gust, you can nicely see it from here in the form of a figure in which you can see the downdraft. But the three main terms that determine the strength of a wind gust is the amount of evaporation that takes place, that determines the so-called D-CAPE value, the water loading term, and the vertical transport of horizontal momentum. Well, if I start with determining the D-CAPE value, then you can derive it graphically from a taphigram or sounding by, let's say, looking at 700 hectopascal. Why 700 hectopascal is just a first estimate, I have to say, because 700 hectopascal is in a lot of situations a layer, especially during summertime, so-called melting layer, where you have your freezing level at that height. And that means that if you, in some certain situation, if you calculate the wet bulb temperature at 700 hectopascal millibar, and you go to the surface along a wet eddy bed, So you take into account that you follow an air parcel downwards to the ground while it is saturated. Then you can determine the so-called downdraft temperature at the ground. And well, the decape is more or less the surface that is spanned between the environmental curve and the downdraft temperature curve. And how bigger that area, how more negative fluent energy is available to cool down the parcel and to that can lead to some certain kind of negative or I have to say acceleration downwards. So that's an indication of, that's one of the terms that influences the strength of a downdraft. So if I go over to a sort of summary, then the three main contributions to downburst strength is the evaporation cooling, the decape, that depends on the lapse rate, and it depends on the dryness of the boundary layer. So you can imagine when you have a dry boundary layer that then a lot of evaporation will take place in the lowest layers, and that will lead to cooling, and that will lead to a net or an extra amount of negative acceleration downwards. Water loading, that's also a factor. So how higher your water content, how more air is moving downwards together with the precipitation. And also a little bit depends on the cape values itself. It's more or less connected to higher cape values, a lot of production of precipitation that will enhance the amount of water loading, and that will also contribute in the strength of the wind gust. And the third term is the vertical transport of horizontal momentum, and that's nothing more than sort of that you convert the high level momentum towards the ground. And when you have a layer which is very unstable, and you can imagine that you have quite an amount of horizontal momentum from some certain height transported towards the ground. Okay, when we look at the multicells, then you see that a typical value of the bulk shear is between 20 and 40 knots, roughly speaking. And you need that stronger shear to have a sort of possibility to re-trigger new cells. And that's shown in this image, in which you can see a typical image of a mother cell and daughter cells. And if you look carefully at this image, you can see that on the right hand side of this image, you can see some daughter cells developing. And that's on the edge of the outflow. And the question I have for you is, can you give me in the chat the reason why new cells are not possible on the left hand side of this image? So you can only see new cells on the right hand side of this image. So please fill in the chat by answering the question why only on the right hand side new cells are possible and not on the left side of this image. And I give you some extra information that on the left hand side you also can see an outflow boundary. And the outflow boundary is visible in this form of blue line. But only on the right hand side you can see new cells. So I will check the chat. And another tip I give you is to look at the shear factor. So the direction of the shear factor, which is very important. And look at the right-hand side also at the rotation couples. And I will explain it to you, of course, in a few minutes. This, I think, is a very important question, because in the forecast office, when you are looking at convection and radar images, it's of course important to determine where new cells are forming. And in this theory of multicells, it's very important that you look up the shear factor. The shear factor is in the direction of where you can see. Well, I explain it to you in a minute by showing you a few images how you can determine the shear factor. What's more? Yeah, I can see the correct answer from Ivona Lelatko. I hope that I pronounce your name correctly. It's the answer. The correct answer is that the vorticity generated by the cold pool has the same direction or sign as the vorticity generated in the air, in the environment. And I will explain it to you in the next few slides. Because when we are looking at the environmental shear, then you, for instance, if you look in the storm relative frame, so you subtract the storm motion factor, and you are sitting in the system itself, then you end up with a wind profile like this. So you can see, for instance, an easterly wind in the lower layers, storm relative speaking, and an increasing westerly wind when you go higher. That produce a rotation coupled like this. That's in this case it's a rotation coupled. I have to say that's anticyclonic. But it's important to realize when you look at the detailed image to the right that if you here you have the cold pool with the outflow boundary, and you can see your environmental vertical wind shear that produces this rotation couple. And if you look at the rotation couple produced at the edge, at the boundary between the cold pool and the environment, you can see a rotation couple that in the middle will lead to an enhancement of upward motion. I will show you that with adding this image. You can see that on the right hand side you have a sort of reinforcement on the boundary between the cold pool and the environment of extra upward motion by looking at those two vorticity couples. It's a sort of vorticity couplet which works together. While on the west side, on the left hand side, you have a cold pool vorticity couple which will damp out the vorticity couple generated by the environment. So that's the reason why you only have on the right hand side, so in the direction of the shear factor, multicells. And that is very important because that's the information you need when you are making a sort of nowcast. So you have one cell, and now it's the challenge that you determine for the next 1 or 2 hours where new cells are forming. So you know where the first cell is, of course, and you have to take into account the shear factor itself. And the shear factor is not always that easy to determine, but if you have a unidirectional wind shear, it's the most easy case. That means that the shear factor is in the direction of where you see the strength of the highest gradient in increase of winds. I hope the alarm at the background will not disturb you, but it's there's an alarm going off outside. It's a sort of exercise we always have on the first Monday of the month here in the Netherlands. It's quite old-fashioned, I have to say, but I hope that you can still hear me and that it will not disturb you too much. Okay, if I go over to this slide, then you can see on the left-hand side, it's not a tornado warning. No. On the left-hand side, you can see three images. You can see, if I start with the upper image, you can see the cold pool on the left-hand side, and on the right-hand side, you can see a clue about the amount of vertical wind shear. And what is nice about those three images is that you can, depending on the amount of vertical wind shear and the extents upwards of the vertical wind shear, you can determine the amount of vertical motion between the environment and the boundary of the cold pool. And well, finally you end up with the middle image, which gives rise to the most strong upward motion, and that has to do with the fact that you have quite a deep layer of vertical wind shear, and you have the cold pool on the left, and that creates the most profitable upward motion. I can see that the text, sorry about it, I forgot to translate the text from Dutch into English, but I hope that you understand the images itself. Well, what is optimal for multi-cell convection, for multi-cell lines, also squall lines, is the middle image, in which you have a cold pool circulation, of course, and you have quite a deep layer of vertical wind shear. And that can lead to quite a perfect balance between the cold pool and the more deeper wind shear area, and that can lead to a quite steep, deep layer of ascent motion. And what you can see from here is that if you look at the wind shear factor and you combine the wind shear factor with the location of the line of convection, then it is the case that when the wind shear factor is perpendicular to the line of convection, then the line itself, the convection line itself, is more or less capable of producing daughter cells just ahead of the main line. And that can lead to a squall line in the best case. And what you can see from this animation is in the upper part a situation with weak shear, and in the lower part a situation with strong wind shear. And what you can see more is in color, a sort of simulated simulated storm. And in white you can see the wind arrows in a storm relative frame. So what you basically see is in the lowest image a situation with strong vertical wind shear that will lead to quite a steep upright area of ascent motion, and that will lead to a continuously grow or development of new cells, daughter cells. But in between, the squall line itself is moving, let's say, from left to right in this image. And so those daughter cells will immediately being embedded in the squall line cloud system itself. So in the end, you only see one major line of storms moving in one direction, and with the help of this process, so that you have an amount of wind shear, but it's strong enough to produce an upright area of upward motion on the edge between the cold pool and the environment. While in the upper image, you have a situation with weak shear, and that shear is so weak that the area of upward motion is not upright, but more over an angle over the storm. So that's not very effective for the development of very strong daughter cells. Well, if you look at radar images, you can see on the left-hand side the initial phase, then a clustering, and a cluster phase, in which you can see this is not a typical example of a squall line, but more a sort of cluster line in which cells are developing along this line. And you can see a continuous development and decaying of updrafts which interact and weaken at the same time or a little bit later. And this is an example that happened in the Netherlands when you start in the initial phase with some very active discrete cells which cluster together with, in the first stage, some large hail and excessive precipitation, and also some high wind gust, downburst. And in the clustering phase, there was a sort of reduced risk of the large hail. And in the cluster phase on the right-hand side, you can see a situation that gave rise to a lot of precipitation in the central and eastern part of the Netherlands. Okay, and the most active phase of a multi-cell, that is when the wind shear factor is perpendicular to the convective line, and that can produce most of the effectively generated and located daughter cells that can lead to a squall line, which can run quite fast. And you need, of course, a trigger. It can be a front or a converging line, and 0 to 3 kilometer shear is typically around 30 knots or a little bit higher. And the line of cells are constantly regenerated along the leading edge of the common cold front of the different cells. It's long-lived. Here you can see some situations of isolated cells on the left, in the middle clustering, and a major squall line that happens in the past over the Netherlands, over the northeastern part of the Netherlands. Well, what is very important again is that when you look at multi-cells, you can have a sort of line with discrete cells which are clustering, but you can also end up with really a squall line. And again, that depends on how the vertical wind shear is oriented, and that give rise to some certain wind shear factor, and that determines if a multi-cell can be converted into a squall line. You can see it on this image. You can see on the left upper image a situation where you have the upper level winds parallel to the squall line. It's more clustering. While on the lower image you can see an angle between the upper level winds, relative winds, and the convection. And that can lead to a more higher risk of severe weather. You can see the situation that happens in the Netherlands with a squall line that's moving from the south to the north, and that's produced especially a lot of wind, because a bow echo can sometimes develop along along a scroll line, and a bow echo is nothing more than a consequence of a sort of internal dynamical process in which you can see a sort of, that also has to do with vertical pressure perturbations, but especially when you have a cold pool circulation below or beneath a thunderstorm, that can create a sort of extra jet in the wind. It's called a rear inflow jet. And those rear inflow jets can develop when you have quite a strong cold pool that produces its own vorticity couplets. And on the edge with the environmental air, those vorticity couplets, together with the environmental vorticity couplets, can produce an extra amount of wind. And together with the vertical pressure perturbations, you can have an acceleration upwards, and that can lead to an extra amount of wind which comes from the back. And OFB stands for outflow boundary. Along such a rear inflow jet, you can you can have all kinds of extra phenomena. Not only the REG, the rear inflow jet itself, but also on the edge, on the boundaries of the outflow. You can also have all kinds of vortices. It can be mesovortices, but also mesovortices. And that's a theory apart. I can talk about it a whole more hour, but then you go into a lot more detail about how vertical vorticity couplets can be stretched in the vertical, and that can lead to some short duration tornadic circulations. So not really a supercell tornado, but more small scale tornadic circulations on the edge of such rear inflow jets. Well, and these can lead to an extra amount of wind, as you can imagine. Well, I think you are familiar with this type of images. It's a very famous image based on a paper, I think some 20 years ago, from the United States, in which you can see the radar echoes, and then the bow segment developing, and then on the edge of the bow segment, on the edges, you can see the areas where you can find some extra vorticity, and that can be stretched, and that can lead to some extra wind, tornadic winds. And in the end, if you look at the system as a whole, you can also see the development of a mesocyclone, and that gives the very significant signature of a comma echo, and that will mostly happen after some hours when the rotation of the Earth, the Coriolis force, determines the shape of the echo in the end. Okay, it's almost 50 minutes past 12. I still have some slides, but I will not go through all slides, but I will leave you with this kind of slides, and I will put this presentation on the Moodle page, and this webinar is recorded, so it will be on the Moodle page as well. So I think there's now room for some questions. So I will go over to the chat, and I will read if there are some questions. What I've noticed in the chat, that some of you gave me the information that on yesterday's convection there was a tornado, confirmed tornado, I think in was it in the southeast of Poland that some of you mentioned? Yeah, east central Poland. There was a tornado report yesterday. Thank you, Alina. Alina Jacek. Yeah.
There is one question in the chat from Luca.
Oh, yeah. That's an interesting question, Luca. Luca Ravnik. Let me see. How much are meso-low and meso-high in convective system associated with hydrostatic balance, and how much with non-hydrostatic? Again, it's a very interesting question. When you look at the pressure distribution, of course, you have to take into account the fact that we have to deal with a non-hydrostatic situation. So that means that you have a lot of vertical pressure perturbations. So there is no balance in the vertical. But if you make an analysis of the surface pressure, you end up with, most of the time, with a quite distinct meso-low and a quite distinct meso-high in a convective system. And if I understand your question correctly, then you mean that how big is your hydrostatic part in determining the formation of a meso-high and a meso-low? That's, I think, your question. Well, I have to say it's an interesting question, but I cannot give you the percentage because in the end you have to deal with a non-hydrostatic situation. So I should say that it is for a great part determined by a non-hydrostatic calculation. If you do it by the model, if you do it by a limited area model, which nowadays are non-hydrostatic, then you end up with a sea level pressure distribution where you can easily find your meso-low and meso-high, and that's based on a non-hydrostatic situation. So So I should say, Luca, that it is more confined to a non-hydrostatic situation or calculation when you look at the models. Even kijken, Daniel asked the URL of the website viewer of EUMETCAL. If you go to EUMETCAL.org, EUMETCAL.org, I can also put it into the chat. Then you see the home page, and then you have to go to the map viewer. And if you send me an email, I can directly send you the URL, but it's not that difficult to find the map viewer itself. But you need to fill in the EUMETCAL.org. Yeah. Van Ole Hendrik, Botvar. Why does the Wikigi layer have to be deeper than the cold pool to have the most effective re-triggering? Have to be deeper. I understand your question. I think, at the same time, you can think, why does it need to have the same depth as the cold pool? Well, I think it has to do with that the environmental wind shear has to be a little bit deeper than the cold pool, because otherwise the upper part of the upright motion will bend too much over the cold pool. So you need to have a sort of extra vertical wind shear just above the cold pool to make sure that the upright motion will remain to be upright, and maybe tilt a little bit towards into the environment itself, away from the cold pool. But that's not too negative for the development of a new cell. So that's the reason why you need a vertical wind shear layer which is a little bit more deeper than the cold pool itself. Yeah, okay, thank you. If you have questions, you can also send me an email to rob.groenland@knmi.nl. And I also invite you to do the exam. That means in the Moodle page you find the Word document. It's a multiple choice exam, and many of you already sent in the exam. So if you do, in the next couple of weeks, I can send you the key exam back with a quite broadened view in a sense of explanation. So I really invite you to do that exam for your own learning curve, because the key exam will give you a lot of more extra information. Okay, it's almost 12:30. And I really would like to thank you all for your attention. And please, I welcome you to do the exam, but also to send me an email if you have further questions, or you would like to have additional information about some certain subjects. So please do so.
There was a question about the deadline.
Yeah, I should say that we start in the week of 12 April. It's now the 3rd of May. I should say that I extend the deadline for 2 weeks. So let's say in 2 weeks from now. So you please do the exam in the next 2 weeks, and also study the other material if you have not done yet. Okay, and Tomislav will put this webinar on the Moodle page.